All right, and we begin. So last time I did the small signal I/O impedance stuff and a biasing overview. I guess there might have been some confusion about what some of the biasing circuits were for, but if you have questions about those, send me an email, and I'll try to at least answer what your concern is about the circuit. So today, I wanted to show you the computer tools, but they're not working. And it doesn't make any sense for me to try to show you something that's not working, because then it just becomes this big fiasco where I'm arguing with the computer about what it's supposed to be doing and it's telling me no. And the studio operator implored me to cancel, but I decided that today we would go ahead and try and do something useful. So I'm going to talk about the design cycle when you're actually building a circuit, and kind of give an example of how the hand analysis is useful. So this is what I'm going to do. We're going to stick with the source follower. Follower. So I'm going to do a little bit more analysis on that circuit. And then if you're going to go ahead and try and design something, you're going to do a first draft of that design. And then on the computer, you're most likely going to simulate, because the simulation on the computer is going to be much more accurate than your hand analysis. But your hand analysis is going to be important to help you fix anything that might go wrong in the computer simulation. So it kind of gives you a window into what might be happening. And then after that, you would basically reiterate. So if you're going through a design cycle, you're going to find out what kind of circuit you need. I'll tell you a little bit about the source follower and why you would choose it. Then you would do a first draft design. Basically pick your transistor sizes, your resistors, your biasing voltages, and then you go ahead and simulate. And then once you got your results from your simulation, you're going to say, is this circuit good enough? Does it meet my demands? If it doesn't, most likely it won't on the first draft. You'll go ahead and try and fix those things and reiterate until you have something that actually does what you want it to do. And we're back. Nope, we're not. Come on. Lapel mics are so tricky, all right? So the source follower that I've been messing with, you would use it in a very small couple of cases. Because basically all it does is acts as a buffer between the input and the output. And its desirable qualities in that respect is it has a high input impedance. Whoops. And a low output impedance. And those are important because if you're thinking of a circuit and you're driving a large load, it basically means that you're going to draw a small current. And a small current draw basically helps you not disturb the circuit over here, right? So when you design, say, an amplifier, you design it with maybe some load impedance in mind, and putting something that has a high impedance in parallel with that load impedance that you designed in there basically won't change the load that it sees much, right? And a low output impedance, if you consider a source that has some output impedance, if you have a low output impedance, this output impedance is going to disturb what you're going to see down here much less. So that's why a source follower, why you would choose a source follower is basically if you have two sections of a circuit that need to talk to each other, but they're mismatched, or one can't source enough current to drive the other, that sort of thing. So back to our wonderful circuit. I'm going to do it slightly different this time to make everybody's lives easier. So this kind of represents my biasing network and my input. I'll talk much more about this when it comes to, whoops, sorry. Let me know if I go off the screen, because I can possibly, continue going and not notice. So I will talk much more about how you get an input on top of your biasing voltage later on. And it's actually really simple, but I don't want to trouble anybody with that at this point. For you guys who came in a little bit late, I was going to do the computer tools today, but they're not working. At least my setup instructions are not working. And I've had it happen before where I've come into class and tried to show people stuff and had one little error, and it just basically wastes the entire period, because it's much harder to debug something for an audience than it is to just kind of do it yourself, And plus, sometimes finding the small little thing that's wrong can take a little while, because you have to go through all the possible cases. So the difference that I'm going to draw here, previously I grounded the bulk. This time I'm going to connect the bulk to the source, and if you remember that I had that other generator that was the bulk to source generator, which basically ended up adding a resistance into my circuit. If I do this, this eliminates that bulk to source generator, because its driving voltage is 0. Right? VBS is 0 now. So that's the circuit I'm gonna mess with. And so, of course, we're going to draw the small signal circuit for this and do all of our wonderful analysis on that, or at least part of the analysis. I'm not going to do the input-output impedance part this time, because I did it last time, and I'm just trying to give you guys an example of the design process here. So hopefully this looks familiar. And this is the generator GMVI. This is the voltage VI. And this is the gate to drain capacitance. And this is the gate source capacitance. And the resistances that I have left are these two from the small signal circuit. So this one is a channel length resistance, and I thought I eliminated that one. We'll leave it in there. Why not? This one I should have eliminated, I believe, because of the generator, the bulk to source voltage generator. Oh, no. I'm sorry. This one came from the fact that I moved this voltage control to CGD instead of CGS, if you guys remember. Sorry. This one we often write as 1 over as GO, but the resistance itself is lambda ID, and this is the Q point current. And then this one is 1 over GM. And then, of course, I have my load resistance and capacitor, RL, and then all of this stuff is grounded on this side. So that's the circuit that I'm dealing with. So before, I didn't want to do the full, whoops, and this is my output point. Before, I didn't want to do the input-output relation, if you remember. But I'm going to go ahead and do that now. It's actually not as bad as I remembered it. I'm going to start with V out. It's GM VI times all of these resistances. So RO in parallel with RG in parallel with what I'm going to call the load impedance. And that's just the parallel combination of these two. So I could have written RL in parallel with CL. But I'm just going to consider that as a separate part. Actually, you know what? I did make an assumption here. From V out? Would it?
That's the impedance in V out.
This part right here?
Yeah.
I forgot to mention an assumption about these two. And basically it's that they're small enough that I can assume them to be open. Is that what you mean? Are you talking about this stuff over here? And the, yeah, okay. So maybe it is as bad as I remember it. CGS and CGD are small enough to be considered open. And again, the reason why I'm doing that is mostly so that I can get through this in a reasonable manner. Once you start considering feedback from within the transistor itself, it gets a little complicated. There are other ways to kind of alleviate that by doing some tricks with how you do the math or how you figure out the transfer function. But we're not really covering those here, so I'm just going to leave them. And so once I've done this assumption, CGD and CGD are small enough to be considered open. So these ones go away. VS becomes VI. And now I'm left with V out over V in is now GM times this parallel combination of resistances. And in order to make my life easy, I'm going to now calculate those resistances as conductances instead. So if I do that, it's the conductance GM, or the transconductance GM, times GO plus GG, plus this thing that I'm going to call the load conductance. Okay. Now the load conductance is basically I'll do it in S terms, but it's basically that. So it's just the sum of those two, and then if you invert that, you will get the standard impedance that you would expect to see from the load. But once I just go ahead and substitute all these in here, V out over V in is equal to GM. So GO is lambda ID, RG is GM, and then GL is this thing that I wrote right here. So it becomes really simple. Lambda ID plus GM plus 1 over RL plus SCL. And of course, usually you don't want things fractions in the denominator. So I'm going to multiply by RL. So we have GM RL, lambda ID RL plus GM RL plus 1 plus SCL RL. Okay. So not much gain there, right? Yet. But let's go ahead and make an assumption that we know that, for example, our frequency is low enough that this is much, much smaller than 1. So the term SCLRL is much, much smaller than 1. And that our channel length modulation and Q point current are small enough to make this much less smaller than 1. So once I do that, if I'm able to assume those two things, and of course I'm going to assume that I can assume those, and lambda IDRL is much, much smaller than 1. Then I'm left with my V out over Vin is equal to GMRL over 1 plus GMRL. And this gets me back to my point of the source follower kind of being a buffer. This is almost 1, right? And in fact, if you choose the product GMRL to be large enough, it can be as close to 1 as you want it to be.
How did you make, you said we assume that big SC is going up so that CL acts as development. And then how did you make the second assumption?
This one right here? By divine intervention. It would really, if you're going to actually build this circuit, it depends on the values that you're going to use.
I thought there's a reason that the ID is 0.
Well, ID is your Q point current, and so it won't be 0 because the transistor has to be in saturation, so it has to be conducting. But what I am assuming is that, for example, my CL might be the gate capacitance of another transistor, so it might be really small because of that, depending on the size of the transistor, right? Or my RL might be really small. And so if my frequency is low enough, that CL times RL times just say J omega makes this entire term much, much less than 1, then I can assume that next to this 1, this SCL is insignificant. And it doesn't have to be, like if it's, 1/100th of a, I'm sorry, 1/100th, not of anything, just 1/100th, then it's probably small enough to ignore for most cases, right? And the same thing for this one. So, we want this to be as close to 1 as possible. So I must make, GMRL much, much greater than 1. And how much greater depends on how good you want it to be. But if we remember what GM is, UN COX width over length times VGS minus VTH. So that's the parameter that we derived last time. So I'm going to go ahead and assume a couple of values from these that are reasonable for a given technology. So I'm going to say that my N-type mobility, my electron mobility, is 219.4, sorry, microamps per volt squared. And that's from the model file that I was using before, which basically describes the physics of the device. So if I use that value, I should get pretty close to what my simulations do and pretty close to what I would expect from a fabricated circuit. So if I want to make GM large, I can do two things. Either width over length goes way up, or VGS minus VTH goes way up. All right. Couple of factors to keep in mind. Increasing the width over the length, or I'm sorry, the width will increase the gate capacitance, the gate to drain and the gate to source capacitance. So if I increase that too much, those might become non-ignorable, and I'm left with something much more complex. So that's that trade-off right there. You don't want these to be big because then that kind of invalidates my entire assumption that I made before. The other thing that I could do, increasing basically the gate to source voltage, would increase, make ID go up, which would possibly make this assumption invalid right here. So there are trade-offs and basically things that you have to deal with to get what you need out of the circuit without running into boundaries that you have to respect, basically. So those are the two possibilities, but let's go ahead and say we are designing the circuit to drive a 50 ohm load. And we want, thank you. Again, we want GMRL much greater than 1. So if I'm going to go ahead and put in 50 ohms into this equation here and see how we can make this greater than 1. Then so I'm left with, whoops, 219.4 microamps per volt squared times 50 ohms times, of course, my width, length, and VGS minus VTH. I want that to be much greater than 1. So if I go ahead and calculate these two values and move them over here, I can find out how big this needs to be in order to meet my supposed design requirements. So width over length, VGS minus VTH, has to be much greater than 91.577. Okay. Oh no, that's kind of big. So if I did it all with my width and length, so one thing I can do is set VGS minus VTH, and that might depend on the technology that I'm working in. If there's a large source voltage available, usually you have maybe VDD is 5 volts, but if you were working in smaller technology, VDD might be 2.5 volts. And in both these cases, VTH is going to be about 0.7 of a volt. So if I were going to look at this case, what I'm going to do would not be possible and have to reconsider. But basically, I'm going to set VGS minus VTH to 2 volts. In other words, VGS equals 2 volts plus VTH. So that's where I'm going to go. So now, if I do that, my width over length has to be this number divided by 2. So 45.58, let's call it that. So my width has to be about 45 times bigger. Why am I saying times 5? Hold on one second. Oh, it has to be much bigger than this. That's why I'm saying times 5. So let's assume that 5 times larger is, quote, large enough. It may not be, right? So if I'm going to assume that this is large enough, then my width over length has to be 5 times this number, or 277 point, about 0.90 times. And if my minimum length is, say, 240 nanometers, or 0.24 microns, then that makes my width equal to 54.7 microns, which is huge, right? So I probably, if I were going to do this, I would probably have to go back and re-examine my transfer function and see what effect the gate to drain and gate to source capacitance are actually going to have. So that's kind of where the hand analysis gets you. So what you would do then is go ahead and simulate this thing in SPICE or whatever tool you decide to use. So from there, you're going to find, maybe your transfer function has, starts dropping off as the frequency goes up. Well, you can go back and look at your input impedance or your output impedance, or both, from last time, or your transfer function, figure out if you're getting a mismatch as the frequency goes up, or if you're, like if we go back to this one, as my frequency goes up, this number is going to become more and more significant, so it's going to play a larger and larger role. So this, I might not then be in a range where I can start ignoring this thing, and I have to take it into account. But that tells you kind of what might be affecting your circuit. And so if I know that my circuit actually does depend on the frequency times the load impedance, or load capacitance times load resistance, I can go back and try and fix that by designing a smaller load impedance, or trying to make RL even larger so that it's less of an issue. But as I said before, if I start making GM too large, GM times RL too large, this assumption is going to get violated pretty quickly. And I'm going to have to go back and actually figure out what the transfer function is going to be with these guys in there. It's not that hard to do that. It's just not exactly fun either, right? But the point is that now that I've done this by hand, I've gotten a first cut at my design. So when things go wrong in simulation, I'm going to go back and look at this stuff and see if I can figure out what is causing whatever trouble I'm having in the simulation. So basically when things are wrong in simulation, the hand analysis basically gives you a clue as to what could be going wrong. So the rest of this, I was actually going to enter this into the software and simulate it, start simulating it for you, or at least show you how to build it. But without that, we're kind of stuck here for the time being. So any questions on kind of what I've done? It makes sense, right? It's kind of straightforward. It's just, I just kind of wanted to provide an example of how you would use, or how you would expect to use the hand analysis once you start simulating. Does that make sense? Kind of?
compare the simulation results with whatever you get theoretically on double.
Yeah, you'll want to, just to make sure, like for low frequency, you would expect to see, the transfer function that I derived, basically. With the possible caveat that, if you did not make this part small enough, you might see some effect from that. But it should be, if low frequency, this term is going to go away. You're going to be left with GMRL. Hopefully lambda is going to be pretty small, so that this term is, if not negligible, pretty close. So you should see a transfer function that's about 1 at low frequency. Now designing for higher frequency takes a little bit more finagling with the stuff, and there's more complex things that you can do. But really, when you guys get to the circuit design project, I'm not really expecting you to do all of the hand analysis on your own. What people tend to do a lot of times is find somebody who's done the hand analysis and try and adapt their design to what I'm asking for. And that works pretty well because, number one, you don't have to do all the complex hand analysis. Somebody else has already done it, and if they published it, it's just been vetted pretty well. And so all you have to do is read what they've done and try and understand it, and then take that into account when you're designing yours. So if they tell you that their output impedance depends on the transconductance and the channel length, as well as, say, the gate source and gate to drain capacitances, then you know where to look if you're finding a bad match with the output. You have a question? No? Okay. And then on top of that, you may have to design a matching circuit between two things, which is it's much simpler than this, but you have to also, for that kind of stuff, you have to take into account the frequency response of that matching circuit. So if you need a wideband match, you have to make sure that you have a wideband match. But in the past, we've only been looking at, about 100 megahertz on a system that's running like about 2.4 gigahertz. So the bandwidth of the matches doesn't have to be that broad for most of these circuits. Other questions? Okay, I don't have anything else. Next time, I'm expecting that I will get a response to my email, and somebody will be able to tell me what is going wrong with my setup, and then we can actually do the tools stuff, and I'll try and get through actually building this circuit then too. And we can hopefully do a simulation and finally see what that starts looking like. And then I think after that, it might be about time to do the Smith chart stuff for the exam. So with that, I will leave you, and we will see you next time.